Welcome back. This is 4-5 Triangle Congruence. Tonight we're going to learn about 3 new acronyms. We already have 2. We got SSS, we got SAS. Now we're going to add ASA, AAS, HL. We're going to have a whole lot of them, and there's going to be even more after this. So here we go. Let's get started. Our first acronym of the night, we have ASA. The ASA postulate stands for angle, side, angle. So we're going to look at 2 angles with the side in between them. That's why it's angle, side, angle. So if you look at your old pictures there, we have our postulate. It's 2 angles in the included side. So the trick here is that we have those 2 angles, so like angle A and angle C, and you'll notice that the side that's congruent is immediately in between them. It's included. It's the side that's part of both of those angles. AC goes between angle A and angle C. Just like on the top one, we got DF goes between angle D and angle F. So that's the included side. So we've got 2 angles with the side that's included are congruent on the 2 triangles. That gives us the 2 triangles congruent without having to find everything else. So you have the 2 angles, they're spaced the same amount apart, you should end up with the same triangle. Let's do an example of this. Another one of these wonderful proofs. We're going to continue doing these for quite a while now. Let's go ahead and get started on this one. We know we're going to be trying to prove that triangle UVX is congruent to triangle WVX. It's right there. It's the proof statement. That's the most important piece of this. To do that, we have 2 given statements. We have the top one, which is that angle UXV is congruent to angle WXV. So let's go ahead and stick that one first. That's going to give us our given statement first. Go ahead and plug that in. We know we can use that. It's already marked in my figure. Don't have to do anything with it. Second given statement, I know that UW is perpendicular to XV. UW and XV. So I'm looking at those 2 lines. They're perpendicular. I can see it's marked. I got a little right angle. Let's go ahead and add that on. UW is perpendicular to XV. Given. Now, what do we do with that perpendicular? Well, I know perpendicular means that they intersect at right angles. So, I know that I end up with 2 right angles, specifically UVX and WVX. One of them marked. Go ahead and mark the other one. Those are going to be both right angles. And I know that because that's what it means to be perpendicular. It means it intersects at right angles. So I end up with right angles, and just like we did last night, if I have 2 angles that I know are congruent, if I have 2 angles that I know are both right angles, I know that they are congruent. So I'm going to go ahead and say that those 2 angles, UVX and WVX, which were both right angles, since we have perpendicular lines, those angles are congruent to each other. Why? Well, because they're both right angles. And right angles are going to be congruent. They're both 90 degrees, so they're congruent angles. Okay, next, let's see what we got so far. We've got 1 pair of angles congruent. We've got a second pair of angles congruent. We're going for ASA, which means I have to find a side that's congruent for those 2 triangles. Well, I can see right down the middle, they got XV. XV is part of both of those triangles. They butt up against each other and share that side. If you remember from last night, we talked about, we have this fancy property for how do we say that that side is shared by the 2 shapes. So it's congruent for both. We're just going to say that XV is congruent to itself. XV is congruent to XV. And that reason, again, was the reflexive property. So we've got reflexive property going on. It's given us that side that we need. We got angles at the top. We got angles at the bottom. We got XV goes between those angles that we're talking about there. Side with angles on either side of it, so ASA, XV is congruent to XV, reflexive property. Last step, triangle UVX is congruent to triangle WVX. So we've got our 2 triangles congruent, and once again, that was ASA. And we got 2 more to do. Next one, another acronym, AAS. This one stands for, you guessed it, angle, angle, side. So it's almost exactly the same as we just did. The difference on this one is that the side is not in between the 2 angles. It doesn't really matter which end of the triangle it's on, it just can't be between the two angles. You'll notice that right here, this congruent mark is not in between the two angles. It's not the GJ is congruent to MK. It's that HJ, which is not between them, is congruent to LM, which is also not between them. So we have two angles and an unincluded side, or a non-included side. So let's do a proof. Here we go. We got AAS. We got a couple things given to us. We'll start off with that. I'm trying to find that those two triangles are congruent. I'll start with the basics. I know that AB is parallel to ED. It tells me right there, AB parallel to ED. I even got to mark those little extra arrows in the little picture. That was given to us. Now, what can you do with that? If I know that AB is parallel to ED, what can we do with those parallel lines? Well, every time we have parallel lines, we can look for those transversals. That transversal, that line that intersects them both. Right there, BD is that intersecting them both. If BD intersects them both, then I can find all those angle pairs that I have. Specifically, the one I'm going to use here is those alternate interior angles. I got one right there, and I got one up here. Angle B and angle D. They're alternate interior. So we know that angle B and angle D are going to be alternate interior. We know that angle B is congruent to angle D. In other words, angle ABC is congruent to angle EDC. ABC congruent to EDC. That's what were those angle pairs again? That's right, alternate interior angles. We got alternate interior angles. We have another pair of those. If you check out over here, going from A to E, that's another transversal. A second transversal doing the exact same thing between the parallel lines. So once again, we got another set of alternate interior angles, just like the first one. We got B and D are alternate interior. We've also got A and E are alternate interior. I'm going to go ahead and name those using the fancy three-letter approach. Got angle BAC, it's the same thing as angle A. It's congruent to angle DEC, that's the same thing as angle E. And once again, that was alternate interior angles theorem. So we got some alternate interior angles. We've got one side that we know is congruent. It was just given to me. Didn't have to do any work for that. So two pairs of angles. The sides are not in between them. Once again, we got the A is congruent to E. We got B is congruent to D. And you'll notice that that side that's congruent, B, C, and CD, those are not in between the angles. That's non-included. So we got AAS, angle, angle, side for my two triangles. All right, last theorem, HL. It's a weird acronym. It's totally different from all the rest. The rest of them are all A's and S's. This one, HL. The difference is that HL is the only one that requires a specific type of triangle. HL requires us to have a right triangle. So the H stands for hypotenuse, that's the longest side of the right triangle, and the L stands for leg, so either one of the other two sides. So with this, there's still three things we have to have. It's just not all in the acronym. One of them is that we have to have right triangles. So we're looking for right triangles with the hypotenuse congruent and one of the legs congruent. We know that the other leg is going to be congruent too because that whole Pythagorean theorem thing. You know, Pythagoras said if we take a squared plus b squared equals c squared, it's going to work for every right triangle. Well, we got two of the sides. I could find the missing one. So HL is just kind of taking that Pythagorean theorem and shortening it down for us so we don't have to find the actual lengths to prove that they're congruent. Let's do an example. This one's a little bit shorter proof, not quite as long as the last two. We know a couple of different things. We know that V and Y are both right angles. So on the little picture there, we know that VW is congruent to YX, also given to us, and we're trying to prove that those overlapping triangles, the two big overlapping ones, are going to be congruent to each other. So let's start off with our given statements. We know that V is congruent to Y, V and Y are both right angles, and we know that that means that they're probably going to be congruent, but I'm going to go ahead and say my other given statement just to get it out of the way. I know that VW is congruent to YX, so that's both givens gotten out of the way. And as I said, I'm going to go ahead and say that XW is congruent to XW. Remember that whole reflexive property thing? It's congruent to itself. Why is that important? Why do we need to say that XW is congruent to itself? I got a pair of angles, I got a side. Well, I'm going for HL. I know that I've got VW, and YX. Those are legs. Okay? XW, if you look, that's this one across from the right angle. That's the hypotenuse. That's our hypotenuse right there. We have to get the hypotenuse congruent. That's the H part. So on step 2, I found my leg, and on step 3, I found my hypotenuse. That's good enough. Now I can go ahead and move on to the last step. Say these triangles are congruent, thanks to the HL theorem. That's it, guys. We're done for the night. Catch you tomorrow.